Okay, page 37, then we move on. Okay, here we go. Conditional probability. Conditional probability of an event B is the probability that the event will occur given the knowledge that an event A has already occurred. This probability is written, this is the nomenclature. This is how we write it. Okay, the nomenclature is the probability of B given A. So this vertical line, right, that vertical line right there, that means given. The probability of B given that A. So the probability that B happens given that A has already happened. Okay? In the case where events A and B are independent, okay, where event A has no effect on the probability of event B, the conditional probability of event B given A is simply the probability of event B. Which means that if you have two independent events, it doesn't matter what the probability of A was. Probability of B is the same. For example, you roll a dice, right? I say, what's the probability of rolling a 4 and then a 6? Okay? Probability A. What's the probability of rolling a 4? 1/6. Okay, probability of B. What's the probability of rolling a 6? 1/6. Do you see how they don't, it doesn't matter what the second one was because they're independent events? Right, so the probability of B, A and B is just probability of A times probability of B. That's it. They're unrelated, so that's your probabilities. Oh wait, going ahead. All right, now, that's kind of the easy part. It gets a little more complicated when you have dependence, where one affects the other. For example, in the homework you did yesterday when you pulled the jacks, and then you pulled the queen, right? You pulled a jack, there's a 4 in 52 chance when you pull the jack, right? Then you want to pull a queen. Well, how many queens are there? 4. How many cards are left? 51. That 51 changed because of the probability of A. So probability of B was dependent on probability of A. It's a dependent relationship. So this is a way we write a more general probability expression. If the events A and B are not independent, then the probability of the intersection of A and B, in other words, probability that both events occur, is defined by, okay, here it goes. Ready? This is how you say this in nomenclature. The probability of A and B is the probability of A times the probability of B given A has already happened. So in terms of your homework assignment yesterday, the probability of pulling a jack and a queen, or a jack and then a queen, is the probability of pulling a jack times the probability of pulling a queen given that you've already pulled a jack. All right? So this is just confusing nomenclature that means what you already know intuitively. Okay, now, let me write it. You could also write it this way if you wanted to. Hold on. You could also write it this way and say that the probability of A and B is also the probability of B times the probability of A given B. So you can flip it around. Knowing that, you could then rewrite and solve for the probability of B given A, which is the probability of A and B together divided by the probability of A, which is unaffected by anything else. So you could figure out what this conditional probability is. You could solve for it. So I'm going to have that equation showing up on all of our future slides so you can use it and refer to it. The first couple is going to seem sort of silly because they're independent events, but we'll take them through anyway. Again, the probability of A given B can also be written this way. Notice the given is what ends up in the denominator. Do you see that? Probability of B given A. The A is in the denominator. That's just the pattern, right? Probability given B, B is in the denominator. All right. What type of conditional probability are we talking about? Independent or dependent? So independent events are things like flipping a coin, rolling the dice, spinning, marbles that you put back, so with replacement. Some cards, in other words, cards when you put them back with replacement. Those are independent events because if you pull a queen and you stick it back, same probability you're going to pull it again. Those are independent events. Dependent events, pulling card and then having to pull another card. Okay? Groups of people, people who make less than $35,000 compared to people who own pets, right? Those are typically dependent events. They are not always. And then varieties and categories. So like, what flavors of ice cream do you like? You know, stuff like that. Okay, so those can typically be dependent. Not always, but they can be. All right, so we're going to look at a problem that we've looked at before, but from this sort of conditional probability perspective, with the nomenclature that you might not have thought about. Okay, so here's a scenario. A die is rolled, and it comes up with a 4. What's the probability of rolling a 4 again? What does your intuition say? 1/6, right? Because it doesn't change. So what we're going to ask is, what's the probability of rolling a 4 given that we've already rolled a 4? Because the second roll is unaffected by the first, you can say that the first roll is the probability of 4 is 1/6, right? That's the first roll. Now we can plug it into our formula and say, well, the probability of rolling a 4 given a 4, here's our formula again, okay? Probability of rolling a 4 given a 4 is the probability of 4 and a 4 over the probability of 4. Now it seems silly because everything cancels out in this case, and you just get 1/6 is equal to 1/36 over 1/6. Duh, right? It's super simple when you're talking about independent events. Here's another example. Oh, it makes me crazy. All right, so if we want to look at the nomenclature in this case, you'd say, well, the probability of A, so the probability of getting 1 heart is just 1/4, right? Because you have 1 out of 4 suits. Probability of A and B is going to be 1/4 times 12 over 51. So if you now want to solve for the probability of B given A, you take the probability of A and B, okay, down here, divided by the probability of A. And so you simplify the fraction, and you get, all things cancel, 12 over 51. It's like, duh, but we already knew that. It's okay. Starting simple, and it's going to get more complicated. Here we go. All right. A bag has 2 blue and 3 red marbles. Likely to be a dependent event or independent that we're going on? What do you think?
Dependent.
Yeah, dependent, because we're talking about marbles pulling from a bag. Dependent events, yeah. A bag has 2 and 3 red. What is the probability the first marble pulled is blue? I'm going to get my stick here. What's probably the first one pulled is going to be blue? Manit, what do you think? 2/5, right, because we had 2 blue. Good. What's the probability the first one blue is going to be red? JD? 3/5, correct. Given that the first marble was blue, what is the probability that the next one is blue? Okay, given that you've already pulled 1 blue, what's the probability that the next one is going to be blue? Luke? 1/4. You got it. What then is the probability of pulling 2 blue marbles from the original bag? Okay, so probably a blue and a blue. Diego, you want to take a stab? Okay, someone want to help him? You think you know, Liam?
Is it 2/20ths divided by 2/5? I haven't simplified.
No. You're overthinking. You're overthinking. Yeah.
Just 2/20ths?
It's 2/20ths. It's 2/5 times 1/4. Do you guys remember how we did tree diagrams? Typically, our tree diagrams have been with independent events, but this case, it's dependent events. Tree diagrams work either way. So in this case, you're going to take 2/5 times 1/4. We want to go blue, right? So 2/5 times 1/4. Okay, so this is kind of using your intuition. Now I'm going to show you the little formula. Here we go. What did we know? Well, the first thing we knew that the probability of drawing a blue was 2/5. What was the probability of drawing a red? This is before any have been pulled. It's going to be 3/5. Okay? Now, the next question says, given that the first marble was blue, what is the probability the next one will be blue? Okay, so how would I write that out? Well, anybody want to take a stab at it? Go ahead, Andy.
The probability of blue given blue.
Bingo! Good job. There it is. The probability of blue given blue is equal to 1/4. What then is the probability of pulling 2 blue marbles from the bag? In other words, what it's saying is, what is the probability of a blue and blue? Okay, well, it's just the probability of 2/5 times the probability of blue given blue, which is 1/4, which is 1/10. what I just did is I just took this, and I took this and put it over here. So the probability of blue and blue is just the probability of blue times probability of blue given blue. Multiplied it out. Now you're doing that intuitively in your head anyway, but now I'm giving you a formula so that when you have complicated problems, you can work them out. All right. So this guy, we're going to try to figure out kind of the nomenclature, what's going on. Here we go. A jar contains black and white marbles. And there are more than 2 marbles. There's a whole bunch of marbles in there. We don't know how many there are. We're just going to give you the probabilities of pulling them, okay? So don't assume there's just like 3 marbles. I don't know how many there are. Okay, a jar contains black and white marbles. 2 marbles are chosen without replacement. What does that tell you right off the bat? Dependent. Probability of selecting a black marble and then a white marble is 0.34. Okay, going black and then white is 0.34. Probability of selecting a black marble on the very first draw is 0.47. What's the probability of selecting a white marble on the second draw given that the first marble drawn was black? Now, how many of you guys look at that and go, ah, I don't get it, this is so confusing, what a mess. Okay, so break it down. You're going to see this on your final exam, you're going to go, ah, so don't, just break it down. Okay, what is it asking? Or what is it telling you? The probability of selecting a black marble and then a white marble. Try to write that in nomenclature. How would you write that? What are you given there? Write it in probabilistic nomenclature. I'll take a volunteer. Anybody wants to take a stab at it? Yes.
The probability of B and W.
The probability of B and W? Correct. Good job. Good. What about the next one? What about the next one? Anyone want to take a stab at the next one? Gavin.
Probability of B black marble.
Just the probability of B, all by itself. Yep. Good. Now, last one. What is it asking us for? What is the probability of selecting a white marble on the second draw given the first marble drawn was black? JD?
Is it the probability of white given black?
You got it. Okay? And the question is, what is that? All right? Now, use our formula. You now know B and W is 0.34, B is 0.47. What is the probability of white given black? Okay, go ahead and try to work it out. Okay, so hopefully you plugged in the values, solved, and figured out that the probability of white given black is 0.72. All right, we'll keep going. All right, now we're going to start looking at some tables, kind of like we did from the homework. All right, so we'll start simple. Here we go. The question is, when you're looking at some data in a table, you just ask yourself, is the data independent or dependent? In other words, is living on campus dependent on what kind of major you have? Or does your major depend on where you're living on campus? Or do you live on or off campus? Okay, so we're going to look at this data and figure out if these two relationships are dependent or independent. And so we're going to test. So the first thing we need to do is figure out what P and A, what the probability of A is, what the probability of B is, and then what the probability of A and B together is. And if it's equal, then they are independent. All right, so here we go. Let's start by finding the probability of living on campus. Okay? Probability of living on campus. In order to find that probability, you go take the total number of kids on campus, which is 200, divided by the total number of kids, 240. So 200 divided by 240. Okay? Next, I want to find the probability of being an engineering major. So think about, maybe mark down right now, what would you do? What would be your probability there? What do you think, Kai?
548.
Okay, give me the overall fraction, just unsimplified, so we can compare it. It was just 36 over...
Oh, sorry. I was at the wrong question.
Okay. Probability of engineering is going to be 36 divided by 240. Okay? All right, next is, what's the probability of being engineering and on campus? Okay? Probability of being engineering and on campus. Hannah is not. Is Hannah here? And Sophie. Okay, keep it simple. Just look at the table. Look at the table. Who in the table is both living on campus and an engineering major? How many of those? Yeah. 30, right? There's 30 of them. Out of how many? No, I want to know out of all people on campus. 240, right? So the probability of being in engineering and on campus is going to be 30 divided by 240. Okay? Now, next one. What's the probability of being an engineering major given that you live on campus? Given that you live on campus. So figure out all the people who live on campus and what's the probability of an engineering major of those people. Natalie, what'd you get? 30 out of 200. Excellent. 30 out of 200, because you're isolating the people living on campus. All right, next one. What's the probability that you live on campus given that you're in engineering? Okay, what would you write for that one? Ty.
Wait, so you're given that it's on campus?
No.
You're given that it's engineering and you're trying to find on campus?
Yeah, so think about it this way. See how it says probability of being on campus given, that line means given, that you're in engineering.
Okay. Wait, so would it be like, so there's the total of 36 engineers.
Yep.
That's given.
Yep.
So people on campus, would that be 30 out of 36?
Correct. 30 on campus out of 36 total. That's it. Good. Okay? I better hurry. I got 4% left. I'm going to die. All right, so here we go. Hopefully this is what you got. Probability of genes. 12 out of 32. Probability of female. 18 out of 32. Probability of genes and female. So that's where you're going to isolate this one right here. Genes and female out of 32. And then genes given female. So look in here, all of the females, 5 out of 18. And then female given genes is female, given that you're wearing jeans, is going to be 5 out of 12. Okay, so let's go ahead and check this out. What's the probability of A and B of being genes and female? That was 5 out of 32. What's the probability that people would wear jeans? Well, that's 3/8. What's the probability that people are female? 9/16. Are they equal? I would do it with my calculator and see what I get. They're not equal. Because they're not equal, you know that they have to be dependent, not independent. There is a relationship between genes and gender. Yes?
So, we're not going to have this formula on the board or anything?
Yeah, I'll probably give it to you. Okay. This one I'll probably get. I'll write it over there. Yeah, this is hard enough. Okay? All right. Now, let's check. Remember the formula, the probability of A is the probability of A and B divided by the probability of A? Okay, let's check that. The probability of B given A would be, screwed it up, probability of A and B, which we figured out is 5/32, divided by the probability of A, which is, what is probability of A? 3/8, and that should equal 5/12. Probability of B given A. So here it is right here. So there's a probability of genes, female given genes. So it should work. That's just a conditional probability formula. It always works, so it better work. But this one over here, this statement, is only true if you have independent events. Okay, I'm going to stop this because that's going to die and close it. Stop.